if you look at this plot, we looked at this plot last time, but we didn't spend much time. You will see that if the number of fins increases, then the heat sink thermal resistance actually goes up a little bit, even without flow bypass. Okay, so this is a minor increase. This is because when you put many fins over an area, then it kind of blocks the flow, so there is a lot of resistance. So that is flow resistance, and along with that there is a thermal resistance also. Now if you have flow with bypass, then you will see that the heat sink thermal resistance goes up quite significantly, because there is not, the heat sink itself is not getting that much flow. Most of the flow is going over the heat sinks, and maybe if there is a side bypass, going by the side also. Right, so in this context, we were trying to understand what are thermal resistance and overall surface efficiency of a heat sink situation. So this we looked at last class. There is this QF is eta F HAF theta B. So this you know, this is based on single fin efficiency. So single fin efficiency, in other words, is the efficiency itself is defined like this, right? QF divided by HAF theta B. So this is all right. What is it, theta B? The entire fin. So this is like for efficiency, you have HAF theta B in the denominator. So theta B is TB minus T infinity. And that is understandable, correct? Why do you use theta B there? Because this fin has the heat transfer HAF theta B. AF is the total surface area of the fin, right? So it is HAF theta B if the entire fin can be assumed to be at temperature TB, right? So that's kind of like an ideal case which goes in the denominator. So that's obviously larger than Q through the fin. So we can write QF in terms of eta F. And then we define a thermal resistance of a single fin also, which is driving temperature difference divided by the heat flow. So it's theta B by QF, which based on the definition of efficiency will look like this. So RT for a single fin is this. So this you can remember that, okay, thermal resistance is got 1 over efficiency of the single fin and then HAF also, right? So based on that logic, there we can define a thermal resistance of the fin array also. We will come to that. Now the overall efficiency of the fin array is Q total divided by Q max. This is similar to the single fin efficiency. So again, what is Q max? Q max will be HAT theta B, right? In case of an array, HAT theta B. So what is AT? AT is the fin area plus what other area did we speak of? Interfin area. We have a name for this. It's always good to have a name. Otherwise, you will say what the area between the fins and this, that. So just interfin area is sufficient. So we use that. So that is A total. And to understand the whole thing, this is A total. Tell me whether this is all right or not. A total is okay. So we have n, obviously the number, multiplied by AF plus AW, and this is AF. What is 2 times L plus T? That's the perimeter. Multiplied by B, that gives you the exposed surface area of the fin, right? And LZ will be that interfin area for one such interfin area, but there are n such interfin areas. So that's why multiplied by n. No, we are taking it to be n only. Actually, it depends on what you are saying is right. Because see, if we 1, 2, 3, 4, 5, 6, and this is 1, 2, 3, 4, 5, okay. But I think the reason why he takes it like this is in some cases it's kind of like this. Okay, so this in any case it will not make a major difference. It's a slight difference only. Anyway, I'm just following the approach that has been taken in the book. So there can be a little bit of area outside this, also on both sides at the base. Right, so this is Q total. And we are interested in overall efficiency of the fin array. So Q total is N times QF plus QW. QW is the heat through the interfin area. And this QF is written, QF is for a single fin, and that is written in terms of the efficiency of the single fin. And then we have QW, which is the heat transfer from the interfin area, just one interfin area. Okay, then we get rid of AW in this stage using AW as AT minus NAF. Actually, N times AW is AT minus NAF, correct? Based on this one. So if you do this a little bit, then you can show that eta O is like this. And I'm sure you can do it on your own. Now, remember that we were saying that resistance is 1 over efficiency times the HA quantity, right? So that is for a single fin, for a fin array. This is the expression that we write. So we are doing all these because sometimes when you make a fin array, you will be interested in knowing what is the overall array efficiency and what is the thermal resistance of that array. Okay, because you made a sink, now you want to evaluate this also. So that's the purpose of doing all this. And one more thing before we go to something else. For a fin like this, which is a rectangular fin, we can sometimes write a corrected length of the fin. Instead of this B, we can write a BC. BC is B plus T by 2. So that's a correction. Why do we need a correction? Because at the tip also there is convection, isn't it? We neglected the convection from the tip, and that's why I derived all this. But after doing all this, now we say that, okay, you can still use the relation for efficiency, right? This is tan, if you write tan hyperbolic MB divided by MB, then that is for an adiabatic tip fin, correct? But we make this correction, so we want to use the same formula, same expression, but considering convection. So we say that, okay, if you consider convection, then we, in the same formula, instead of B, we write BC. So BC is B plus T by 2. So this we are not going into in great detail, but these things can be proved. In any undergraduate book, you will find this discussion also regarding the correction. So if you have a convective tape, we say BC is B plus T by 2. And MBC can be shown to be something like this. And eta F, single fin efficiency, is, as I told you, this quantity. Right, so we have done a few things about heat sink. So what have we done so far? We have essentially looked at rectangular fins. And for rectangular fins, we have considered natural convection as well as forced convection. And we have considered not only the fin equations, but we have also optimized the fin array. We have optimized a single fin, whereby we got that beta equal to 1.4192. We've been spending so much time on that. But we have also, in the last lecture, as well as some of the calculations that we did yesterday, we looked at optimization of a fin array. So that optimization of a fin array also, we got some optimum value of the spacing between the fins, and thereby the optimum value of the number of fins. And we also got a beta value for an entire fin array. So we saw yesterday that optimization for a fin array gives you a beta value which is quite close to the beta value of a single fin, right? So these are some of the conclusions that we have done. There are some limitations also. We have just looked at this kind of rectangular fins, right? This sort of thing, rectangular, which essentially looks like this. But in reality, there are other kinds of fins also. There are radial fins, circular geometry. And there are all sorts of other types of fins. But the idea of discussing rectangular fins is that it's kind of like the geometry is a bit easier, and then whatever we have learned using rectangular fins, in theory, in spirit, it kind of works for circular fin also. Just the equations will change, but the approach will essentially remain the same. We cannot cover everything in a course, right? Okay. Now, we will, after this, go to a fin, again a rectangular fin, but in the fin that we are going to consider, radiation is also important. Now, some of the fins that we discussed, they were going through natural convection. There was natural convection in the fin. But when there is only natural convection, that means there is no forced convection, then the radiation can also compete with natural convection. You kind of know this, right? Natural convection heat transfer coefficients are low, like 5, 10 watt per meter squared Kelvin. So that's not a very good number. If you have forced convection, you can easily go into hundreds, can even cross 1000 watt per meter squared Kelvin heat transfer coefficient. So if you have forced convection, radiations cannot sometimes compete with forced convection. But if you have natural convection, the radiation sometimes can compete easily with natural convection. So radiation can be important. Now, when are fins more useful? Fins are more useful when you have lower value of heat transfer coefficient, right? Because if you have quite a high value of heat transfer coefficient, then maybe you don't even require fins. That's why when you have flow in a tube and then water flowing inside, there is air flowing outside, you place fins on the air side, because on the air side the heat transfer coefficient is smaller, correct? Now, typically in many cases you have natural convection, you have low heat transfer coefficient. That's why you are adding fins, but then radiation can also come into picture. So let's look at a situation like this. So you take 30 seconds to read the figure. What does it say? This looks similar to what we had seen before. I mean, this sort of figure we had seen before, correct? See, you have to say something, right? You have to say yes or no. Shouldn't keep quiet. I mean, this is not a very complicated question. I'm only asking whether you've seen something like this before. Okay, you've seen something like this before. Now, what are the differences that this figure has with previous similar figure? Radiation, right? How do you know radiation is included? Emissivity is mentioned. Okay, that's one. Then Q double prime top and Q double prime bottom, right? And DQ radiation is also there. And the interesting thing is surroundings are at 0 Kelvin. In this figure, this is some representative figure. The surroundings is 0 Kelvin, not 0 centigrade, 0 Kelvin. Why? Because this is an example for space applications. So when you have this satellites and International Space Station and all that, there will be generation of heat there, right? Because people go there and there were astronauts, cosmonauts, even staying there for a few months, okay, a few weeks. So their body metabolism is one, but there are also like electrical appliances, there is power module, and there's generation of heat, right? The heat needs to be dissipated. Otherwise, it will accumulate heat. So, in space, do you have convection? No, you don't have convection. Why? So, deep space means like you don't really have many molecules, very, very few maybe. Okay. So, there is no flow around that module, around the space station or satellite or whatever. So you cannot dissipate heat by convection. That's a problem. You can dissipate heat by radiation, but you want to increase that area through which the radiation will take place. Well, radiation will also depend on area. So that's why you add fins. Now, one good thing is that the surroundings are at 0 Kelvin, again approximately. Why? Again the same thing, that you hardly got any molecules out there. See, if you don't have many molecules, see, the temperature relates to the kinetic energy of the average kinetic energy of the molecules, right? See, if you hardly have got any molecules, then the temperature will be close to 0 Kelvin, right? So the heat which is getting generated inside that space station or satellite or whatever, from that heat can be dissipated to the to deep space, right, which is at 0 Kelvin, and that can be done by radiation. So these things have to be designed very well, isn't it? Otherwise there is problem. Everything that goes up in space has to be designed perfectly. You cannot make mistakes. If you make mistakes, the whole thing will burn off and people will die and all sorts of things can happen, right? One error and everything is gone. Okay, now what we will do is we have this slice again. So this is the differential element. We call it a differential element. And in that differential element, that slice that you see, there is again qx going in and qx plus dqx going out, right? As we usually do for a fin energy balance. But there is no dq convection in this case. There is a dq radiation, which is shown in the figure. dq radiation. So there is some heat which is going in, some heat which is going out, but there is a dq radiation also. In addition, there is q double prime top and q double prime bottom. Where is the radiation coming from? Radiation will come from other celestial bodies, like it can come from the sun, it can come from the from some other planet or whatever, right? Some objects from a very long distance. Radiation can travel without a medium, right? And even if that's very far away, it can still come, right? So there is a q double prime top and there is a q double prime bottom. Okay. Emissivity is something which depends on the material of this, obviously. Now we can write these equations. So again, have a look at this and tell me whether this is all right or not. These three equations. And I suggest, this is not much, so these only three equations, please write those also in your copy. So this should be all right. What about this one? First equation, I think nobody has any problem with this. What about the second one, dq rad? So the top, on the top you get a surface area which is this strip, the top surface area, which is dx. This thing is L. So area is L dx, right? And L, I think he's taking L equal to 1. Okay, L equal to 1. Just considering unit width. So if you so this is the area, and then there is two such areas, top area and the bottom area. So then we have epsilon sigma A, right? We should multiply this by t to the power 4 minus t surrounding to the power 4. So T surrounding is 0. That's why it turns out to be something like this. L equal to 1. Okay. So you use this in here and then you can show this. Fine. What are our objectives now? We are doing this uh, for the case of radiation, and our objective will be very similar to what we had done before when we didn't have radiation. So our objective will be to maybe get the temperature profile, how temperature changes with X. We know that the temperature will go like this. Okay, but we want an exact expression, not just qualitatively. We want actual numbers on this one, right? The whole thing, some expression for this. Temperature as a function of X. But we also want to find out other things like maybe efficiency, etc., etc., and the heat flow, not just the temperature as a function of X, but also the heat flow, heat which flows through the fin. Plus, we will also try to get an optimum design, like what we did for other fin cases, for minimum fin weight, or you can say volume. Right? For a material, for a chosen material of given density, weight and volume are proportional to one another. So we want to do all this. Now, this is the expression. Okay, so this is maybe I can write it here, the last one. And then we can integrate this one. And this is integrated from x to b. B is the tip of b is the length. So at x equal to b, you got the tip of the fin, right? And we are also assuming dt dx equal to 0 at x equal to b. So adiabatic fin. Okay. And after that, we take dv equal to d2t dx 2 dx. Just a substitution which is going to be useful. And v equal to dt dx, right? V equal to 0 at x equal to b, and v is just v at x equal to x, a general value of x, right? So if we carry out the integration, we'll get something like this. And then we get this expression. Now, rather than me explaining everything term-wise, can you just go through this yourself right now and tell me whether these things are okay? This seems all right. So this d2t dx2 dt dx dx, this term, this is the first term, that's just this, obviously, right? So that is utilized here, and this term after integration becomes something like this, and this is this one. So this should be okay, right? This is the right hand side. This one should be the right hand side. So we got this equation after multiplying this one by dt dx, and then we integrated it, right? And from here, of course, we can get dt dx because this is dt dx squared, and we can get a dt dx. But you can see that dt dx has been obtained by taking a square root, correct? So my question there, which I've written on the slide, is that why do we have a negative sign? Correct. So that's a good answer. Because the mathematics, as the mathematics tells you, it can be plus or minus both, right? But we are using physical reasoning to say that it cannot be plus, because dt dx has to be negative. Temperature has to decrease with x. Temperature has to decrease with x. So we have chosen a negative sign. Yeah. So that's dt dx. And we can also get qf. How do you get heat transfer qf? If you again think about your undergraduate heat transfer, I mentioned this in this course also, that there are two ways of getting heat transfer from a fan. One is that, okay, you say H in A T minus TB and T minus T infinity, and then H T minus T infinity dA, and you can integrate this, right? Because the heat transfer takes place by convection from here, from the top, from the bottom. And so if you do H delta T dA and then integrate over the entire exposed surface area, then you will get heat transfer. That is one way of getting it. But what's the other way of getting it? Through a fan, heat transfer through a fan. What's the other way of getting it? I think you are not revising at home. You want quick answer. Because this is undergraduate stuff. This you have done before. I touched upon this also. Honestly, are you looking at the notes going home? Here also you will not say anything. You'll keep quiet. You have to look at your notes on the same day. Like whatever I'm doing today, whatever you're writing in your copy, you should have a look at that for 10 minutes, not, I mean, you won't need to spend more than 10 minutes time. 10 minutes, you just glance at your notes, then it will stick to your mind. If you don't do that, it becomes more difficult. Okay. Last chance. What is another way of getting Q? Correct. Okay, so that's the answer which I should have got much earlier, and I should have got from everybody, and within 3 seconds. Okay, so this is QF, this is QF. So obviously this is just QF equal to minus K dt dx minus K area at the base, and we are calling it AB or something. Okay, whatever is the area. dt dx at x equal to 0. X is measured from here, so here, isn't it? Whatever is going in through conduction at the base, that same thing gets dissipated by convection from the sides, right? From the top, from the bottom, from the sides, from the tip also. All right, so that's the heat transfer. And we got this expression for QF because we already had an expression for dt dx, previous slide. And that dt dx we use here to get that QF expression, which are marked 1 on the slide. As you can see, there's no point deriving everything in class. That's just a loss of time, right? So this is QF, and from dt dx, so we have a dt dx expression. From dt dx, you can just say, okay, separate this thing dt and dx, and then integrate. Okay, so dt dx equal to c or something, actually not c, some function. So dt is that function times dx. And from that you can separate and you can integrate and we can get x, right? So that x will have this integration involved in it. And this one is from t to t base. Okay, now let's see the notations. What is t? What is t? At? No. So the T is the temperature at any x. So there is a general x, which is somewhere, okay, variable thing, and that gives you a temperature which is T. So that's a general notation. This x is general, this T is general, but at that x, correct? Now, the notation thing is important because there is a T base. What is that temperature? T base is this temperature, correct? And this one we are calling T at B. So be careful. Be careful because you shouldn't mix the two. You shouldn't think that TB is T base. It's not that. All right, so this can be obtained by integrating the expression for dTT, separating the variable and integrating. So we get this. And since this is for some general x, it will also be valid when x equal to b, right? So this thing, when evaluated x equal to b, gives you this expression, which I'm calling as equation 2. Right, so what has happened from this equation to this equation? What has happened is this t has become tb, this x has become b, right? And the rest of it is the integration part, which remains the same. So these are two equations, 1 and 2. Now, if you look at these equations, they have got some equations 1 and 2. They have got some dependencies. So they are dependent on QF, EQF, B, TB. So they depend on these things, 1 and 2. Correct? Again, what is it that we are trying to do through these equations? What is the objective? Because sometimes when you look at these equations, after a while you forget what you started off with. What was the plan, right? Yeah, so you want to get the temperature as a function of x. I mean, these are obvious things, like when you have a pen, you want to get temperature as a function of x. You want to get QF, correct? So these are the initial steps. Then you also want to optimize for maybe a constant mass, which is like constant volume, hmm, which in fact becomes constant profile area, right? Not constant, I should say prescribed, given value. So these things we want to get, right, in the presence of radiation. So we'll also notice that in the presence of radiation, the equations have become a bit more complicated. So there are funny things like temperature to the power 5, because he started with temperature to the power 4. You got temperature to the power 4 because Stefan Boltzmann law says that Q is basically from uh, Planck's law. After you do some integration, you get heat transfer as epsilon sigma area times T to the power 4 minus T surrounding to the power 4 for a simplified case. Okay. Otherwise, there will be view factors also, and you have to do a more complicated analysis. For a simple case without view factors, etc., it's just epsilon sigma A Ts to the power 4 minus T surrounding to the power. So that's why these equations are complicated. Much more complicated than what we had for just a pure convection case. Right. So these are complicated equations which have to be solved. Now the other problem is that we have two of these equations, number 1 and number 2, and actually 2 is a case of the middle equation, the x equation. But they are dependent on these things. We have 2 equations, we have got 4 of these unknowns, so obviously there can be multiple solutions. Very large number of solutions. How do you solve this? So this is something which I suspect I will not be able to do much about in today's class. There's just no time. But I want you to read this problem statement, which we will take up in the next class. So for the next few minutes, just read this. And then I'll tell you a little bit about this problem. Really nothing new. It's the same problem that we are talking about, just some numbers have been given. Okay. But here, this last sentence is something new in the sense that it defines a problem. So you have to get the minimum volume by providing the fin thickness and profile length, volume, temperature at the tip, efficiencies for 3 heat dissipations per length. So there's this QF, some QF values are given in the problem. So 150 watt per meter. 150 watt per meter, what is that length? Heat dissipation per unit length. So that is at L dimension. L is taken to be 1 meter. So that 150 watt per meter, somebody tells you that, okay, I want 150 watt per meter. So this is like this fin goes to some satellite, and then some amount of heat has to be transferred. Let's say this 150 watt per meter. Now design the fin. That's the challenge, right? So we will work with these equations. Remember, this was the governing equation, and then on integration we got something like this. This is QF. QF again obtained as minus Ka dt dx at the base of the thing, right? And we got this sort of expression. This is B, again, nothing new. So this is an example problem in the book in which the author has described solution of this. He solved this using a software called MathCAD, which, to the best of my knowledge, we don't have access to in IIT. I don't think we have a license of this. We have other, like some Mathematica and stuff, but we don't have this. So you will not be able to understand exactly what he has done just by reading the book. But even I have not used MathCAD, but I'll tell you what essentially the author has done with these equations. Without going into MathCAD, what broadly he has done. So these are the properties, the base temperature, the thermal conductivity, etc., etc. This is the heat flux at the top, 80 watt per meter square. Then heat flux at the bottom is 30 watt per meter square. The profile area is just B into T. We know that AP is B into T. He uses this notation here to mean that he has used MathCAD. So there's a colon and then an equality. So this is not, this is just MathCAD notation or something. I mean, he implies that when he writes this, he has used MathCAD. Okay? That means that expression he entered into MathCAD. But don't bother. What he gets is that if you get the profile area as a function of fin thickness, then these are the curves that you get. So let's say 150 watt per meter. So looking at the results, 150 watt per meter, and this is kind of a curve. So it tells you that around here, you got a minimum profile area, which will correspond to this much fin thickness and this much profile area. So that he has got by solving these equations, which of course we can do only on Tuesday. Okay, thank you.